today. The good news is the last cycle, I think, is a fairly straightforward one, although we do introduce a new method to fix states on the in the vapor compression refrigeration cycles. But I think that it's almost a little bit fun, right? If you can call thermodynamics fun, right? The other thing that we talked about last class was that I want to go into these review sessions with students bringing in problems. So I would like to talk about maybe which cycles do you want to review in these sort of 2 to 4 review sessions that we have left. So I'm happy to take input either through the chat or if you want to unmute yourself and we can discuss.
I found one problem in the textbook, and it deals with the Brayton cycle.
Cool. So
it was problem 9.84.
Oh, don't tell me, because you surprised me on the day.
Oh,
right?
True. Right. Okay.
Because that way you get to see sort of how I would go about doing a problem that I haven't seen before.
Right. Okay.
Right? So so maybe if you can, I don't know if you can take a picture of it or something with your phone, and then you can
actually.
So we'll do perfect. Right. So we'll do a Brayton one. Right?
Okay.
Are there other cycles that you feel like maybe you're worried about or that you'd like to review for class or in class?
Maybe a turbojet problem.
Yeah, so turbojets I think are a good one too. So if someone can volunteer, so Dan's already sort of volunteered to find one problem. If somebody could volunteer to find a turbojet problem for us, I would appreciate that. Okay, so that's good. Yeah, one with an afterburner would even be better, right? So Sebastian, and then I do think that the Rankine regeneration cycles tend to be difficult. So we'll do Brayton on Tuesday. We'll do a turbojet on Wednesday. I don't know, we can take requests again after that, but I do think that Rankine regeneration is one that people tend to find difficult because you have to find that value of Y. So I think that's good, or just some complicated Rankine cycle. That'd be a good one to do, but maybe we can talk about that next week. So at least we've got Tuesday and Wednesday ready for next week. And then we'll, maybe once we get to Tuesday, we'll start looking at Thursday and Friday. Does that sound good? Yeah, a Brayton cycle with everything. So it sounds like Dan has found a Brayton cycle. So I assume that it's one where it's going to be a significant number of processes, right? So not just like a 4-component Rankine cycle. I imagine it's something exotic. And it might be a little bit more like that turbojet problem that we did last class, where I more talk about how to fix the states. Depending on how much information is given, I might not be able to actually get numerical answers for all the states and talk you through it, right? Just like on an exam, you're not going to get like a state table that has 10 states with 4 of them as isentropic and real, so it's really like 14 states. Like I'm not going to make you do 10 of the 14 states, right? So maybe, I don't know, maybe 8 to 10 of them would be filled in, and you get to demonstrate your understanding of how to find the rest. So that's good. At least we've got a plan for Tuesday and Wednesday, and then we'll kind of refocus then next week. So that's good. Thank you for participating. I appreciate volunteers. So today we're going to start to talk about vapor compression and refrigeration, right? So, we've been talking about, sort of creatively putting together these Lego pieces to make cool stuff, right? So today, right, because it's, again, maybe my kids are too into Disney, right? But it's sort of like, we're trying to learn how to build a snowman here, right? So what we're trying to do is, how do we get temperature to move or heat to move in the direction that it wouldn't naturally want to move? So all the other cycles that we've talked about up until this point are heat engines, right? So most of them are talking, when we're characterizing them, it's net power divided by heat in, with the turbojet being a bit of an exception, right? Because it's trying to find thrust power. Here, the benefit is going to be some heat transfer term, and the cost is going to be some power in. So we'll start to talk about coefficients of performance. Now, these cycles are also going to be open systems, right? So when we talk about our three big questions, right, it's, how do we characterize the system, right? So these will be some heat transfer term over some power in, so there'll be coefficients of performance. And then, is it open or closed? So these will be a series of open system processes, right? And then it's going to be, what's the fluid, right? So the fluid will be more like water. So the answer to the questions here are, again, mostly like the Rankine cycle, except the first one is different because we're going to characterize the cycle differently. But first, these are all a series of open system processes that we will end up, putting together in series. Then we're going to do the first law to find things like power and heat transfer rates, right? But, we're also going to have to, potentially, right, when we were talking about this class, right, we said, when you're doing these open system analyses, sometimes, right, you can't have like this perpetual motion machine, right? So sometimes we have to deal with the second law too, right? And this was kind of our first introduction into these heat transfer type cycles, right? Because first, when we talked about the second law, we talked about it in terms of the equation, right? But then we talked about it conceptually, and Kelvin and Planck were talking to us about heat engines, right? And they said, yeah, you can make a heat engine that takes heat in and turns it into work, but you can't turn all the heat into work because you have to have some kind of a heat sink. You have to keep your engine cool, right? So that means you can't turn all the incoming heat into work, right? And that totally made sense, particularly, I think, when you're talking about things like locomotives, right? This idea that, you give mechanical engineers heat, and what we want to do is boil water, right? Because that can give us mechanical power, right? That's where the word thermodynamics comes from, right? It's using heat energy to get work, right? And, again, the classic example of this, right, is the locomotive, right? The steam engine, right? And then, like I said, I kind of got disappointed, or, depressed is probably too strong a word, right? When I found out that, this nuclear power plant, which is like, in some ways the pinnacle of human technology, right? We're really just generating a bunch of heat to boil water, right? It is just a steam engine. It's just we found a way better way to make heat, right? But, maybe at a similar time when we were, trying to travel all the way across the US, right? We were thinking about how do we preserve food too, right? So, you can salt things, right? So you can, like bacon, you can do this with, right? You cover it in salt, right? And you can preserve it that way, right? You can smoke stuff. I made ribs on the weekend, right? Which was delicious. It's, my brother lived in Texas for a little bit, in Austin. He did a postdoc there, and which is like an apprenticeship to become a professor. And, when he came back, he wanted to, he lives in Binghamton now, actually, so close also in the United States. And he called me one day and he's like, should I buy this smoker from Oklahoma that they're going to ship up, and it's a big, thick steel wall or whatever. And I was like, well, because you're calling me, that means that you want the answer to be yes, because the other option he had was to call my dad. And my dad's normal first response to ideas that we have is, don't do that, it's stupid. So, right, so because he was, maybe you have that same experience, right? But because he was calling me, I think that meant that he wanted the answer to be yes, right? So that's kind of a personal finance thing, but you gotta like the things you like too. You gotta have rooms for, you can't just squirrel all your money away, which is maybe sometimes the problem that I have, right? But then, when I go into the basement of my grandparents' old house, right, they had this cold cellar, right? So this room that was kind of dug out in the basement that wasn't insulated to the ground outside of it, right? So it was kind of a cold room, right? Because it's below the ground, right? So even in the summertime, it would be reasonably cold, right? And that was another place where you could put stuff and it would stay cold, right? So something like, this cool room, right? So you'd have these canned goods, right? And you could put them in there and they'd stay a little bit longer, right? So then right? Maybe somebody, and this, I'm obviously just making this up, right? But, somebody like Clausius maybe comes along and says, well, this cold room thing seems to be a good way to keep food for a while, right? Can I make a device that does the same thing, that makes this room cold, right? Because, what the universe tries to do, right, is take a cold space and equalize it, right? Because what happens is, right, heat is going to flood into that cold place from places with higher temperatures, right? So then Clausius looked at the second law and he said, well, it's impossible to construct this device which operates on a cycle whose sole effect is to transfer heat from a cooler body to a hotter body. So what this is kind of saying, right? And again, I'm not a huge fan of this verbal definition, right? What he's saying is that, yeah, we can make a machine that takes heat out of the cold place and transfers it to a hot place, but we can't do that and produce work, right? We can't even do that and break even. In order to do this, we have to put work into the system, right? So essentially what we do is we make a machine, and the machine's got like two parts, right? When I was a kid, McDonald's had this hamburger called the McDLT, right? This was back when they used to package stuff in styrofoam, right? And, one half was hot and one half was cold, but because it was like in styrofoam, it was like hot side hot and the cold side cold, and you put it together, right? I don't know, right? That was the marketing, right? But this is kind of the same thing, right? Where this machine has a hot side and a cold side. And what we do, we don't actually break the universe here. We're not really transferring heat from a cold place to a hot place. Instead, we make a machine where the cold half of the machine is colder than the cold place. But then there's a hot side of the machine that's hotter than the hot place. So we're not breaking what my old heat transfer professor used to call the 0th law of thermodynamics, that heat always flows from a higher temperature to a lower temperature. We're just making a machine that has a cold side that's colder than the cold place, right? So if you look at your fridge, the coldest part of your fridge, of the actual apparatus that does the refrigeration, is colder than the air inside the fridge, right? So it's removing heat that way, right? And this is one configuration for a vapor compression or for a refrigeration cycle. So this is called vapor compression refrigeration, right? In the same way that a Rankine cycle can produce power by bouncing back and forth across the vapor dome, this vapor compression refrigeration cycle also bounces back and forth across the vapor dome, right? So here, it's almost like a Rankine cycle, right? But we're running it in reverse. So here we have the cold side temperature. This is what the refrigerator is trying to do, right? Remove heat from our cold reservoir, the cold place. The way we do that is that we're friends with some chemical engineers who've made some refrigerants, and they're fluids that boil at very low temperatures, right? So we run a heat exchanger here with this refrigerant running through it, and it's taking heat in from this cold place because these refrigerants boil at lower temperatures than our cold place, right? And so the heat comes in and we boil this evaporator, so our quality is going up, right? And then we have a vapor over here and we move into a compressor, right? So now we're going to increase the pressure. And then over here, we're going to condense the fluid. So we're going to reject heat as we condense the fluid. So we're going to go from a vapor to a liquid. And then we go through this expansion valve, right? So there's heat exchangers, but the heat exchange is like, if we do a Rankine cycle, it would look different. The arrows would be going the other way, right? We'd have a pump over here and like a turbine over here. But everything's kind of flipped around in these refrigeration cycles. So here we're adding heat at the bottom. We're rejecting heat at the top. Instead of getting power out on the vapor side, we're putting power in. So this is a compressor instead of a pump. And then here, instead of the pump, we have this expansion valve. So at least for now, we'll think about this as a turbine, as a place where, because the pressure here is going to drop on the liquid side, we at least have the potential to produce power here, right? So the thing about the refrigerator, right? And we talked about how refrigeration cycles and heat pipe cycles are kind of the same thing. It just depends on your perspective. So we're really going to learn 2 cycles today, but they're the same cycle, right? The difference is when we're talking about a refrigeration cycle, we're interested in how much heat is leaving our cold space. Our heat pump cycle is going to be exactly the same, but our perspective is going to be up here. How much heat are we adding to the hot space over here? So refrigeration cycles, these are always 4 component cycles. They're always the same component. So this is not like the Rankine cycle or the Brayton cycle, or even I guess the turbojet, where we could increase complexity. These are always going to look the same, right? That doesn't mean the question always looks the same, but the cycle looks the same. So if we were going to draw the TS diagram, it looks kind of like a Rankine cycle TS diagram, but we're going the opposite direction, right? So we'll draw this all under the vapor dome, although, you know, in practice, maybe that's not the best way to run it, right? Just like when we started talking about the Rankine cycles. But if we did this all under the vapor dome, right, then at state 2, I could have saturated vapor that's coming into my condenser and saturated liquid that's coming out, right? So the condenser goes from a saturated vapor, in this case, to a saturated liquid, right? So this also happened in the Rankine cycle, right? But we were doing it on the bottom half of our curve, right? Because everything's kind of inverted in this TS diagram, right? So this is our condensation process. Now, if we had an ideal compressor, then in order to get from our low pressure here in the evaporator up to our high pressure here in the condenser, we vertically move up from state 1 to state 2S, if this compressor was ideal. Now, when we go through the valve, it's not an ideal process. So I probably exaggerated how much this line slants as I move from the left to the right, but I'm trying to explicitly show that this is not like an ideal turbine. This is not an isentropic process. Delta S is not 0, so this is not a vertical line. And then in this case, our evaporator is just moving from state 4 to state 1, adding some heat. Now, in real life, probably you want to go from state 4 all the way to state 1 up here, and then come all the way up here. But I wanted to stay all the way under the vapor dome in this particular drawing. Right, so this looks like a Rankine cycle, kind of, right? So the first thing is that instead of moving clockwise around the cycle, right, now we're moving counterclockwise around the cycle, right? Because this, you know, I think of these cycles as Rankine cycles in reverse. The other big difference is we don't have this vertical line as we go from 3 to 4. This is not isentropic. We'll see that it ends up being something different, right? And it actually ends up being easier than a turbine, right? But for now, we'll just say that it's not isentropic. So it's like a Rankine cycle, but we're running it in reverse. Right? We're putting power in at the compressor. We're rejecting heat through the condenser. We're going to say for now that we're producing power in the expansion valve, that it looks kind of like a turbine. We're at least going to approach the first law that way. And then we're going to add heat at the evaporator. Right, so I got 4 processes. My heat exchangers here, I'm interested in heat transfer rates. And my power terms, they're going to be at the compressor and the expansion valve. Right? Now, this is what's different about these heat transfer cycles, right? Is that there's still energy benefit over energy cost, right? But they're not thermal efficiency, right? The characterization parameter here is a coefficient of performance. For refrigerators here, you can write COP, maybe subscript R, or if you want, you can use the Greek letter beta. I remember that beta goes with refrigeration cycles because a B looks kind of like an R, right? Now the thing is, the energy benefit is going to be, for refrigeration cycles, the energy benefit is the heat that gets removed from the cold side. So this is the heat at the cold side, or the evaporator heat rate. And then the energy cost is going to be our net power. So if you've ever run an air conditioner or a refrigerator, you've probably realized that it doesn't work very well if you don't plug it into the wall, right? Because this compressor needs to be driven, right? So it's requiring power. So here the energy cost is going to be the net power that we put into the cycle. For the coefficient of performance, I'm not showing it here, but these, we can always talk about these as in terms of absolute values if we want as well. So how are we going to go through and do our first law analyses for this cycle, right? So all of our components are going to be at steady state. All of them are one inlet and one outlet, so it's not like Rankine regeneration. We're going to neglect kinetic energy changes, so it's not like a turbojet. We're going to neglect potential energy changes like we've done in all of the cycles. And then for each component, we're going to say that it's adiabatic and or passive. We're still going to neglect friction as we're transferring heat and in between all of our components. And we're going to neglect heat loss in between all of our components as well. So this is a pretty common assumption set that we've had, right? And if we can make all these assumptions, we're going to get the equations that we recognize, right? Or hopefully that we're coming to remember for W dots and Q dots, right? So here there's 4 components. So there's 4 different equations that I'm interested in. The compressor, which is consuming power, right? So this is going to be m dot times H in minus H out. The valve, at least for now, because I know that heat transfer is not important in the valve, but I do have that pressure change. So maybe I'm producing power in the valve. So I'm also going to model that as m dot times H in minus H out. And then the evaporator and the condenser, where I'm transferring heat, that's going to be m dot times H out minus H in. If we did conservation of mass on all these components, because they're all chained together, they're all one inlet and one outlet, and they're all at steady state, we're going to find that all these mass flow rates are the same, right? So even though I have different subscripts on these m dots, they're all the same. Now here's the thing. This is why the valve is different than a turbine, and potentially why it's easier than a turbine, right? So the first thing I think that we want to remember here is that, remember when we did Rankine cycles, that the back work ratio was really small, right? And at the time I was saying things like, oh, it doesn't take us much work or power to increase the pressure of a liquid, right? Now, the inverse of that, or I guess the other side of that coin, is that when we're dropping the pressure of a liquid, we can't get much power out. So instead of putting another component in there that's a turbine that's got to be like, manufactured, it's really difficult, it drives up the cost of our refrigerator or our, what's it called? Air conditioning unit. We're going to assume that this valve is isenthalpic. Now, if you remember, isenthalpic means that there's no change in the enthalpy, right? So it's not isentropic, where there's no change in the specific entropy. It's isenthalpic, where there's no change in the enthalpy, right? So that means that it's easy. Once we know state 3, we also know state 4, because state 3 and state 4 are the same enthalpy. They have the same H value. But that also means that the power produced by the valve is 0. So if you actually look inside, especially in older fridge, maybe now they do it differently, but oftentimes there's just this little thin copper tube that's coiled around in this kind of serpentine path, right? Or maybe a helix, right? And it's really just there to drive the pressure down. It's not really doing anything. We're just trying to get a pressure loss to bring that pressure back down to the same pressure that we want the evaporator to run at, right? So the valve is very boring. It's only the pressure that's changing. There's no enthalpy change, right? There's no power that gets produced. So when we look at this cycle, we know that the compressor is consuming power. That's why we got to plug your fridge into the wall. The condenser is removing heat. That's the heat transfer that happens on the hot side. And the evaporator, which is what we're interested in a refrigeration unit, is taking heat in from the cold side, right? There's no power associated with the valve. All that happens in the valve is there's a pressure change. Now, because this is a refrigeration cycle, when we talk about the coefficient of performance, we get the heat transfer at the evaporator, that's the heat transfer on the cold side, divided by the net power. But the cool thing about the net power is that it's only one term, because the power in the valve is 0, and the power in the compressor is going to then be something, right? So when we talk about our coefficient of performance, it is Q dot on the cold side divided by the net power, but that's really just Q dot on the cold side divided by the power consumed by the compressor. Now, because Q dot is positive here, Q dot on the cold side, heat is coming into our system, and the compressor is consuming power, then this would be a negative number, but nobody wants to buy a refrigerator that has a negative coefficient of performance because that seems bad. So instead, we just take the absolute value of these things. The coefficient of performance will always be positive. Now, if we wanted to then take the real coefficient of performance and compare it to the ideal coefficient of performance, then if we know the temperature of our hot place and our cold place, remember these are temperatures that are outside of our cycle, right? Then we can define our maximum or our Carnot coefficient of performance as T cold over T hot minus T cold, right? We know that the actual coefficient of performance has to be less than the Carnot coefficient of performance. The other note here is that, especially in the numerator, I think anytime you're doing these Carnot parameters, always change to Kelvin or Rankine, because then you'll never be wrong. At least you'd never be wrong for that reason. But certainly the numerator here has to be in Kelvin or Rankine because it's not a temperature difference. So that's how we do refrigeration cycles, right? Now, what about heat pumps? The good news is heat pumps are the same thing, right? It's the exact same cycle. The only difference is we characterize it a little bit differently. Because if I'm looking at a heat pump, really what I'm interested in, I can use this same type of cycle to run and heat my house, right? So there are people, if you live in more moderate climates, I think, than we have here in Rochester, right? Because it's, this is kind of what happens in the Northeast, right? We get really cold winters and really hot summers, right? But if you live in a place with moderate climates, you can heat and cool your house with this same apparatus, right? They just run it in sort of opposite directions, right? So, you can use it to heat your house in a mild winter and then to cool your house in a mild summer, right? But because we got sort of extreme winters and extreme summers here in Northeast, typically you have two different devices in an air conditioner and maybe a natural gas furnace, right? But the difference between the heat pump and the refrigerator is the energy benefit, right? So it's going to be the numerator in our coefficient of performance, right? So here we're going to have Q dot out or Q dot in the condenser or Q dot hot divided by net power. But the analysis is exactly the same, right? It's still the same 4 components. It's still all the same assumptions. We're still going to get all the same equations. So if I do my heat pump analysis, I'm still going to get the compressor power is m dot times h in minus h out. The valve, there's no power, there's no heat transfer associated with the valve, it's just pressure loss. The condenser and the evaporator are going to be m dot times h out minus h in. But if I'm talking about a heat pump, the energy benefit, the heat transfer that I really care about is the heat transfer on the hot side, right? Which is the heat transfer in the condenser, right? This is the heat that gets rejected from the condenser into the hot place. So now my coefficient of performance looks a little bit different. Now instead of beta, we use gamma. But if you just want to say COP, subscript heat pump, or something like that, that's fine, right? It doesn't really matter the variable name that you use here. It doesn't even really matter conceptually if you're talking about a thermal efficiency or a coefficient of performance. All of these things are energy benefit divided by energy cost, right? So here in the heat pump, the energy benefit switched from the refrigerator. So now instead of Q dot on the cold side, it's Q dot on the hot side, because we use these heat pumps to heat up the hot place. But the energy cost is still the same. The heat pump you also have to plug into the wall, or I guess maybe into some kind of solar panels or geothermal, whatever, right? So it needs power to go in, right? I guess you could hook it up to a hamster wheel too, if your hamsters can run fast enough to run your compressor, right? You need to put mechanical power into this system, right? So now our equation is a little bit different for the coefficient of performance because it's the other heat transfer that we're interested in, right? Here I still put absolute values on this, but here both of these values are going to be negatives. So for the heat pump, because we're losing heat out of the, this is the condenser side, and we're putting work in. So both of these numbers are negative. But if you just get in the habit of knowing that coefficient of performance always has to be positive, that's good, right? And again, we can compare this to the Carnot equation, and it looks almost like the Carnot equation for the refrigerator, but now because our benefit is heat transfer on the hot side, our numerator in the Carnot equation is the temperature on the hot side. So this is our equation for heat pumps, and then our equations before for the condensers, right? So hopefully at this point, right, because you've done Rankine cycles before, this is very similar to Rankine cycles, right? So, except that the characterization parameter is different, right? It's also a lot like Brayton cycles, right? Except the fluid is different, right? And the characterization parameter is different. So once we get to this point, when I talk about kind of our general solution method, right, then, I say something like, now is the time, right? We've done our symbolic solutions. Now we got to fix the states, right? So we ask ourselves the question, what's the fluid, right? So for these, so these are the equations for heat pumps and refrigerators. It's the same equations, right? It's the same components. It's just the heat transfer term that we're interested in for both of these things is different, right? But it's the same cycle, right? So now we're at the point, we've got our symbolic solutions, and we ask ourselves, what's the fluid? Is it ideal gas? No. It's not even water, but it's something like water, right? Because for these refrigerants, right, we've got a thing called an evaporator and a thing called a condenser. And those two words imply to us that there's phase change. Evaporator, that's like we're boiling fluid, right? Condenser, that's like we're going from a vapor back to a liquid. We're condensing it, right? So this isn't water. It's going to be some kind of a refrigerant. But it's, it's like water in that we have to ask ourselves, after we know that the fluid is some refrigerant, then we know that this has to be a phase change process. We got to ask ourselves, what's the phase? Just as a side note, it's good that we know chemical engineers because, they're always working on better refrigerants, right? This was one of the things when I was a kid, people were worried about ozone layer depletion. So this is a problem that I believe NASA has said that we've mostly solved, that the ozone layer is either closed or closing, right? This was sort of a good example of us using science to figure stuff out. And one of the things that we did, in addition to changing how we did aerosol sprays, was we moved away from refrigerants like Freon. So chemical engineers were working on different chemicals, different refrigerants that still boiled at low temperatures, but didn't have maybe the environmental impacts that other refrigerants had. Right now, I think we usually talk about 134A in this class, HFC 134A. I don't know what the trade name of that is, but I think they moved on from that too. We had a problem with a leak in our refrigerator or our air conditioning unit last summer. And of course, your air conditioner only fails on like the hottest day of the year. So we replaced our air conditioning unit, and it's now to Preon, I think is the name of the new refrigerant, the newest refrigerant. But it does kind of, there's obviously an economic cost to changing these things too, because we could have just sealed the old unit and, refilled it with whatever the refrigerant that was in it, right? Which wasn't Freon. It was this HFC 134A, I think. And but they don't make that chemical anymore, right? Because the environmental regulations become tighter and tighter, right? So it was pretty expensive to redo it. So we might as well just get a new system. So that's kind of that's cool, right? So we have a comment from Dan that they're working on manufacturing ice machines, right? So they're definitely, so you're doing this is close to home for the people that are working there. That's pretty cool, right? So so now what's the fluid, right? The fluid is like water in that it's going to bounce back and forth across the vapor dome, but they're different tables if we were going to use the tables. But we're going to try to learn today a way that we can fix these states graphically without using the tables, right? So if you got a question like this on the exam, right, you could use the refrigerant tables that are in the textbook, right? So maybe you go to the, I would tell you whatever refrigerant it is, right? The table, the textbook does have tables for 134A, so that's probably what we would use, right? I think most of the questions in the textbook talk about 134A. And you could do it just like water, right? So you'd ask, what's the fluid? You'd maybe have to look if you were going up through that condenser, right? So you'd find the value of, say, if it was isentropic, right? You'd say that, S2S is equal to S1. And then you say, is S2S, is that going to be such that we have a superheated vapor, or is it going to be a two-phase mixture, right? And then once you knew that, you could find quality. And when you know quality, then you can find H, and then you're good, right? Because then you can answer the first law. Today, we're going to talk about these pH diagrams, which are sometimes called Suva tables. If it's an ideal compressor, you need to know that that it's then isentropic, so that delta S across that ideal compressor is 0. Real compressors, then you'll have to know the isentropic efficiency for the compressor. Right? Remember, compressors are like pumps, so the ideal compressor goes on top because it consumes less power than the real compressor. Going through the valve is nice because it's isenthalpic. Delta H is 0. So once you know H3, you also know H4 because they're the same. So if we're going to find this graphically, we have to use this graph, right? Or a graph like it for whatever refrigerant you're working with. It's a little scary because there's so many lines on this graph. This is like, if you take Thermo 2, you'll relax our assumptions about gases a little bit. So we usually think of air as just air, when in real life, air, it has some humidity in it. It's some combination of air and water, or water vapor. And in Thermo 2, you'll probably talk about the chart that's got the best name of like all engineering charts. It's called the psychrometric chart. And it helps you find enthalpies and things in air, because air is really a mixture of air and water. So that's pretty cool. But this one is kind of scary too, because it's got so many lines on it, right? So I'm going to walk you through this, right? So the first thing is, this is a vapor dome. This is a scale diagram showing us the vapor dome, right? But it's not a TS diagram or a TV diagram or a PV diagram. It's pressure on the vertical axis and enthalpy on the horizontal axis. So this is a pH diagram, right? And it says enthalpy, but it's really specific enthalpy, right? So when we look at these graphs, it's pressure versus specific enthalpy, even though it calls itself enthalpy, right? And the cool thing about this is, on that graph, you get basically all the information that you get in the tables, right? But it's all on one sheet of paper. So I think the advantage of this is if you're in the trades, if you're working on air conditioning type problems, you can kind of do them pretty quickly on site. Now you have to accept that there's some uncertainty when you do this, right? But this will at least put you in the ballpark. Right? This chart, it labels the different values, but it never uses the word specific. So if something, we got to remember that all the variables on this graph are intensive variables. So they should all say specific in front of them, unless it's something like pressure, which is just naturally intensive, right? Just like temperature. right? So pressure is absolute pressure. It's not gauge pressure. Enthalpy, right, is really specific enthalpy. Temperature is just temperature. Quality is just quality. It says entropy on the chart, but it's really specific entropy. And it says volume on the chart, but it's really specific volume, right? And if you check the units, you get that too. So how do we deal with this graph, right? So first we got to know how to read the different things. And it's not too bad. It's like a normal graph when you're looking at the vertical axis. So if you want a constant pressure line on this graph, it's a horizontal line. So when we're going through, say, the condenser or the evaporator, we typically assume that that's a constant pressure process. So we will be moving along a horizontal line for that constant pressure process. If we want enthalpy, the great thing is if we can fix a point, yeah, it does seem a bit overcrowded, right?
At one point, do you not? At one point, do you think maybe this is a little much on one graph?
Oh, but the great thing is we don't have to do any interpolation, right? So it's definitely an easy graph. I'll give you that, right? So if you get a problem like this on the exam, my advice again, which has been pretty consistent, is try to use color pencils and maybe use different colors for different things, right? So because there's definitely a lot on this graph, right? So we're going to try to walk through it so you know which data goes where. And I think when we do the example next class, so next class, please have a look at the starter sheet when we're doing that. So before next class, download, and if you can, print off the starter sheet, because we'll solve it using one of these graphs. And I think that it's better if you can do that. And I'll use one that's got a higher resolution than this one. This one, the lines are a little bit pixelated, right? So specific enthalpy lines are constant. Specific enthalpy lines are vertical. So if we ever, the cool thing is, right, to fix a state, we need two independent intensive properties, right? So we want two lines. Now, two lines meet at a point. So where those two lines meet, we'll fix our state. That'll be our state point. And then we can draw a vertical line down to get the specific enthalpy. Right? Now, there'll definitely be uncertainty when you read numbers off this graph, but you can do it pretty quickly. A lot quicker than if you're, doing the interpolation for everything in the textbook. Here's where things get a little bit crazy, right? So constant temperature lines, you can see them over here. It's a little tricky, especially again, because the resolution on this one is not great. So when I look for constant temperature lines, the first thing I always want to do is find 0, right? Because sometimes if I just look quickly, it's not immediately clear that this is -10 and this is 10, right? So if we find 0, anything to the left of 0, temperatures go down as we move left and up as we move right. So here, these are in Celsius and not Kelvin, right? So that's why we have to worry about positive and negative. So these lines generally go down and maybe down and to the right a little bit until we hit the vapor dome. Right? Because under the vapor dome, temperature and pressure are dependent. So then it's a horizontal line across the vapor dome and then down again. Right? So if you're drawing a constant temperature line, this is what it looks like. Quality only exists under the vapor dome. This just looks like our normal vapor dome where 0 quality, right? Saturated liquid is on the left-hand side. And as we move across the vapor dome here, right? 0.1, 0.2, 0.3, these are the quality values, right? And then eventually you get to the right-hand edge, and that's saturated vapor. These, I think, are the ones that are the hardest to read, the constant specific entropy lines, because they're not quite parallel over here, right? They diverge a little bit. They're even a little bit curved, but these constant entropy lines are over here, right? And if I'm looking for a value, these are the values of the constant entropy lines down here. Constant specific volume, they only show outside the vapor dome, right? And it looks like, to me, it looks like, hairs sticking up off the top of a hill or something like that, right? Or long grass blowing in the wind. Starts being vertical, but then gets up and starts to curve to the right. So if I want the specific volume data, it's over here, right? And over here, this one says, oh, this one has units, right? So this is meters cubed per kilogram. Okay, so that's how we read the chart, right? Now, how do we fix a state? right? So if we want to fix a state, we need to know how to draw these constant lines, right? Because if we have two independent intensive properties, then we can fix a state, right? Because two independent intensive properties gives us two lines. Those two lines should only come together at one point. That one point is our state point, right? So we'll draw two lines, and where they meet, that's our state point, right? And then once we know the point, we can look at all those other lines and get estimates for what the other values are. Now, because we're mostly interested in the first law, then it's the vertical line down that we're mostly interested in to find H. But sometimes we'll be interested in the second law, and then you got to look at, or maybe just we're going through an isentropic process and we want S to be the same at two different pressures. So you might have to sort of estimate about where you are there. Right? Now, it's important to remember that if this is on an exam, I'm going to grade the process. So you're going to want to submit a picture of what your diagram looks like. But I'm not going to be super worried if the numbers are off by a little bit. Right? So it's the process that I'm grading, not the number. Right? And this can happen in particularly in second law problems, where depending on your uncertainty where measuring S, you might get that the process is possible or not possible, because often there's not a lot of wiggle room between a positive and a negative sigma dot. But I don't really care what your answer is, right? I want you to go through, do the process, find an answer, and then, often it'll say in the next part of the problem or the same part of the problem, is this thing possible? And then you look at your answer, and if the value is positive, you say, yes, it's possible. And if the value is negative, you say, no, it's not possible. And this is the other thing. If you don't have a number, right, these ones are gimmies anyway, right? Then you write, I don't have a number, but if sigma dot was positive, this would be possible. And if sigma dot was negative, this would be impossible. I don't care if your answer is right. I care that you demonstrate your understanding of how sigma dot tells you if something is real or not possible, or ideal, I guess, if it's zero, right? So here we're going to do an example, just a quick one for one process, right? So this is a heat transfer process. We're doing an evaporator here. We're going from state 1 to state 2, and we're evaporating some fluid. So we start at state 1 with 5 bar and a quality of 0.2 or 20%. So it's 20% vapor. And then when we're done, we're still at 5 bar. So this is a constant pressure process, and our temperature is 20 degrees Celsius. And we're going to try to find the heat transfer rate divided by the mass transfer rate. Right? So here's our control volume, right? We're looking at just one side here, so we're not going to cancel out Q dot. Conservation of mass tells us we're at steady state with one inlet and one outlet, which means that there's only one mass flow rate. Then there's the first law part of the problem, right? So we're going to say that this particular component is steady state, one inlet, one outlet, no kinetic energy change, no potential energy change, and it's passive, right? We're also going to neglect friction loss. There's no really lines that we're worried about, but I wrote this down anyway, probably because I just copied this slide from above when we were talking about the whole cycles, right? So maybe unsurprisingly, we get to this point. Q dot is equal to M dot times H out minus H in, right? That's H2 minus H1 for us. But we want Q dot over M dot, so really we're going to find delta H. So now we have a symbolic solution, right? And we got to say, what's the fluid? Oh, it's a refrigerant. Because it's a refrigerant, now I have this graphical chart. So I'm going to find H2 and H1 graphically using one of these pH or SUVA diagrams. Right? So I don't know Q dot, I don't know H out, or I don't know H in. Otherwise, I'm great, right? I got the right equation. I just don't know anything. Right? So we're going to try to get some numbers so we can get a value for Q dot over M dot. And to do that, we need to fix the states. So we're going to start with state 1. The nice thing about this is we know 2 pieces of information about both of these states, right? So we don't have to know anything really about the process, right? So let's find state 1 first. So we know that it's 5 bar and a quality of 0.2, right? So here's our diagram. Remember, it's a vapor dome, right? And because they're giving me quality, I know I'm going to be under the vapor dome somewhere. So first, it's 0.5 megapascals, right? So then here, right? I look, this is a log chart vertically, right? So these are not evenly spaced, right? So that there's a different, right? It's a log scale, right? So 0.5 is over here. It's not quite halfway. It's a little past halfway between 0.4 and 0.6, right? So this is 0.5 megapascals, right? That's my constant pressure line. But now I need to find quality equal 0.2, right? So now here's my quality only under the vapor dome. There's the 0.1 line. Here's the 0.2 line, right? So I draw this line here, and I get my point over here, right? So now I know where this point is, and I can draw a vertical line down, and I can get H1. Now, there's a really important thing to notice here, that H1 on this graph is 260 kilojoules per kilogram, about, right? But if I look this up in the textbook, I get that it's 108.8, right? So what the heck, right? Why is it wrong, right? It's not exactly wrong. It's just that enthalpy is a little bit like temperature, where, it makes sense as delta H, right? The first law is always telling us about delta H. But you can have different zero values, just like you can with temperature, right? And pressure, right? You can have zero temperature at where water freezes, or you can have it where the molecules stop moving, right? So here, the reason there's a different zero value is just how they're set up, right? So they use different conventions, right? What this means is that we can't use the textbook for half the problem and the chart for the other half of the problem. We either have to use the textbook all the time or the chart all the time, right? We can't use both because they're separated by about 150 kilojoules per kilogram, right? So, if I add them both together or take the difference between them, it's like taking the difference between a temperature in Celsius and a temperature in Kelvin. Even though they're the same quantity, you just can't do that without converting them, right? So either use the graph or use the textbook. Don't use both, right? So now we fixed state 1. Let's find state 2. So state 2 is also at 0.5 megapascals, but now it's at 20 degrees. So here's my 20-degree line over here, right? It comes down, but it hits the vapor dome before it crosses this pressure line that we have, right? So we got to go all the way across the vapor dome before this starts going down again. And here we see that it meets somewhere over in the superheated vapor region, right? So now we can draw a vertical line down and we get a value, right? So here I'm going to say that's about 412. If you were graphically doing this, maybe you would have a different number, and that's okay. But if I look this up in the table, it's going to tell me 260.4. Either number is fine, but it's like Ghostbusters. You can't cross the streams, right? You got to be either the chart or the textbook tables. You can't go back and forth. So I'm going to prove to you that it doesn't matter if you do it on the table or in the text, right? So now we have delta H. We have delta H on the tables and delta H in the textbook, right? So we're going to get values for Q dot over M, right? If I use the chart, then I get that Q dot over M dot is 152 kilojoules per kilogram, right? And if I do it in the textbook, I get almost the same thing, right? Now, my numbers are all different, right? But they're offset by the same amount, right? So this means, at least in this case, graphically, I chose pretty good numbers, right? But I would not expect the agreement to be this good. I think here I just got lucky, right? So if you're doing this by hand on the graph, you're probably going to have more uncertainty than that, right? But these two numbers should at least be in the same ballpark, right? Depending on whatever your graphical uncertainty is. So that is all that I had for you today. I apologize for keeping you for a couple extra minutes. You can't just eyeball the number. You can bust out a ruler and look between those lines and say like, oh, it's, 6 millimeters to my point and, 15 millimeters to my, between the two lines, so that, you can kind of get it. Or you can just sort of pick a number, it's about a half or a quarter or 20% or something. I'm less concerned about the number that you get on the exam when you're doing this and more concerned about the process that you have. So don't just write the number, right? You got to upload and submit your your actual graph that you did the work on. All right, everybody. That's all I have. Does anybody have any questions?
Have a good rest of your day.
You too. So thank you.
you.
Tomorrow we'll do a problem like this using the graphs with, I can't remember if it's a heat pump or a refrigerator. All right.
Sounds.
Bye-bye.
Thank
everybody.
you.